All right, so I'm going to start now. So I'm going to try to give an overview of the data reduction method, and I'm going to try to give some introduction to what you guys are going to look at carefully during the hands-on session. So I'm going to try to stay broad and not to get into too many gory details, at least in that part, in the first part. In the second part, I'm going to go a little more freestyle, and we'll see if I have time to go through everything. So the goal of this presentation is to give you a flavor of how we're getting these pretty pictures of planets around other stars or disks around other stars. Starting with raw data that doesn't look anything like this. I mean, you wouldn't have any idea that there's anything like that when you look at the raw data on these sources. So let's start with some equations, but it's not too complicated. So let's think you have an image, all right? And your image, it's some realization of some random telescope image. So this is the image of a point source if you have no astrophysical signal. And this psi here lumps anything that can go wrong with your image. So it could be speckles, it could just be photon noise due to limited integration time. It could be during your exposure, you have a little drift in pointing, and that just messes up your image. Anything that can go wrong. That's not astrophysical. And then this would be some astrophysical signal here. And of course, you don't know which one is which. You just have this information here. So the goal is to kind of remove this, make this equal to 0, and make this appear. And the epsilon here is 0, 1, of course, because you don't know. If you have epsilon equals 0, there's no astrophysical signal. If there's 1, you have a planet or a disk. But a priori, you have no idea what's going on. So how could you go about it? You could have a really, really, really good model of the instrument. You model the hell out of your systematics, and you know what this is, and you subtract it. You calibrate that. You could construct a really good model of the instrument based on the data history. You have some telemetry, you have some PSFs, and you're just trying to put everything together, and you estimate this. And once again, if you can remove this, then you have your signal. Or you could just get more realizations of this random variable here, of your telescope response function. And you get a bunch of them. And based on those, not knowing anything else about what the hell the instrument is doing, you try to reconstruct this number here. And this is really what I'm going to talk about. In the end, I might graze into these methods. And this doesn't mean that these methods are bad ideas. These people are looking into them, and they show some promises. But for now, over the past, let's say 6 years, most of the community has been focusing on going through this process here. So that's what I'm going to go over, and that's what you guys are going to go through during the hands-on sessions. So let's start with a simple way to do that. You take the image of another source. So whether or not there is signal, it's one image minus the other, right? It's pretty simple. You need the telescope in the instrument to be very stable. You want them to be exactly the same in a perfect world. And then you need to, in particular, when you have a coronagraph and the star is not exactly the same place, you need to align them very, very, very well. And Carol is gonna discuss that during our session. And the main problem here, so this is an ICMOS image, this Hubble. So as stable as it gets, it's in space. I mean, there's only so much. I mean, you still have the breathing, but that's as good as you can get. And still, look at this. It looks the same. But when I flip between one and the other, you have all these little residuals here. And these little residuals, they're much bigger very often than any planet you want to find around the star. So you can still do a lot of it with this technique. And with being more careful, you can find all these debris disks. And Hubble has been really a workhorse. I mean, this is not NICMOS. This is STS this time around. It's a paper by Glenn Schneider that just came out. And you can really do amazing disk science with this technique. And even if most of my talk is not going to be about this, it's going to be about more recent methods, this is something that you should keep thinking about, in particular in terms of disk science. So the other method is to say, well, I can't really take images of more sources. I want it to stay very stable. So I'm going to look at the same star. But now, what I'm going to do is I'm going to have the astrophysical signal move on the focal plane array while the systematics, which is these speckles here, all these blobs here, they're just coming from the star, they're not planet light, while those stay fixed. And this is an image from the Gemini Planet Imager. And this is the ADI observation method. where you let the sky rotate on your detector. So I don't know if you can see this here. This is beta pictoris B. And your planet is turning, but your speckles stay fixed. So now you can think, well, I'm just going to try to take patches of the images here where my planet is not where I'm trying to subtract the speckle, and I'm going to do something magic, and I'm going to be able to find my planet very neatly. So that's this case where the realization of the instrument doesn't move, and then the astrophysical signal, which is a companion in this case, moves. You can go the other way around, and you can make your the realization of your instrument move and your companion not moving. And when you do that, you actually can play this trick of changing the wavelength. So this is an integral fluid spectrograph data. And here you're changing the wavelength, so you're seeing that everything is stretching as a function of wavelength because diffraction goes as 1 over lambda. And your companion here stays fixed and doesn't move. So that's a second observation strategy that you can use in order to build more knowledge about the instrument. And the third one here, I'm not showing pictures here, but you take simultaneous image and then you modulate the signal in and out. So it's like this little yellow horrible beta that appears or disappears if you're colorblind like me. You can see it actually. But you can, for instance, you can modulate the speckles with your AO system. And in the part of the field that's going to be modulated, everything is going to change except that your companion is not going to be coherent. So whatever, it's not going to be modulated by your optic system. Or you can play games with polarization differential imaging. But in any case, I mean, I hope what I tried to convince you of here is that this is the first step, and it's called what I like to call an observation strategy. Figure out a way to have images where either you're sure there is no signal and on the other images you might have signal, or if you can't do that, if you don't have these type of references, well, at least have the signal a priori moving on your detector. So it's doesn't hit always at the same place. Once you have that, you can say, well, I'm going to build a model of my systematics of this on the pixels where I know for sure that I have no signal. And this is mostly where all these methods, they've really started in the early 2000s, one way or another. But really the part where once you have built that knowledge, you're really trying to optimize your empirical model of the instrument response function, which is this problem here. This is something that really started in the past 5 years. And that's what I'm going to be insisting on in this talk. So you have your target image, in which you have your instrument response function and then your hypothetical astrophysical signal. And you have a set of reference images. And note that in the reference images, I'm saying there is no astrophysical signal. So this means that you might have to choose your images a little bit carefully, or the regions of the images you're choosing. But let's assume you're doing it properly for the sake of the argument here. And all you want to do is you want to reconstruct this term as a linear combination of these references here. And so you want to minimize in the least square sense, because we like least squares. It's really nice. It behaves very, very well. And computationally, it's nice to matrix inversion. You want to find the best linear combination of your references that match your target image. So that's the least squares problem. Oh, let me try this. So how do you go about it? So you can kind of draw a cartoon. You take a piece of your image that works well with the observation strategy that you've chosen. And that's your target images. Your target image here with k pixel on your image. You take the same part of the image in all your references, and you're trying to find the right coefficients. You're subtracting those two. And you're trying to minimize this in the least square sense by integrating over the pixels here. All right? So when you do that, what you're doing in practice, you're taking a column matrix of your reference library, a row matrix of your reference library. You're multiplying those two. So what you're doing, in fact, you're building a covariance matrix. All right? And you're saying that this covariance matrix multiplied by your coefficients that you're looking for has to be equal to the covariance between your references and your target image. And this is just, you take the least squares, you take this equation here and you just derive this. It's a tiny bit of algebra. Okay, it's simple. So we've solved everything, right? We're done. And we're not done. And here's why we're not done. And this is all about inverting this matrix and inverting an ill-posed matrix. So I'm going to try to illustrate it. And because first time, not actually, second time trying it. So hopefully it's going to work out. Stop me if you guys don't follow. Let's assume the case of an image with just 2 pixels. Just have 2 pixels, all right? So this is pixel 1, this is pixel 2. And your instrument realization is these blue lines, all right? And you know that the signal is going to look something like this. Whatever, that's your planet on those 2 pixels, it looks like this. But of course, you don't know what it looks like. All you have is another image that sort of looks like this. That's kind of close to those. And what you're doing is you're calculating the covariance of these, and then you're trying to invert them and subtract it in order to find your signal. Well, your system is ill-posed, so your green coefficients are going to go completely bonkers. All right? The matrix is not invertible. There is no reason why this number couldn't be minus 10,000, even if we know in reality there is no reason in the instrument why it would be minus 10,000, but the matrix inversion doesn't know about it. And so what you're done with something that's completely in the signal, and the detection is really not really nice, because that's the red arrow is what's left after you've done your Psf subtraction. Now, if you start putting regularization into the problem, that is, you're a little bit careful about how you're inverting the matrix, you can find something, a red arrow, that's your residual after your Psf subtraction, that sort of looks like the signal. It's not exactly like the signal, it sort of looks like the signal. And all this game in the literature that you're seeing about different algorithms, all this stuff, it's getting as far away as possible from this case and as close as possible to this case. And I'm going to show you through the rest of the talk a bunch of different variants of how to do this, but this is pretty much 95% of the story. And this is another way to see it. So this is an image of a disk seen with NICMOS. So this is the Psf Subtraction Image. So you see there's this very, very nice ring here. And there is this extended halo here, which is real. You just don't see it in other images. And this is just done with Psf subtraction. So it doesn't, Psf subtraction gives you the nice ring. So in that case, I'm meaning Psf subtraction straight up, target reference, nothing else, nothing fancy. Now here, you build the entire covariance matrix and you invert it. And you can see that you can retrieve the ring. And you can really clean up the image close to the star. So here you have all these blobs. You had no idea, maybe there is a planet sculpting that ring. Well, here you can say, no, there's nothing here. But you've lost all the properties that when you try to model your disk are super interesting to estimate the scattering properties of your grains in your disk. You're done with that. You don't have the information anymore. If you do the regulation properly, then you can carve out the hole and still rule out any planet and get the diffuse halo in order to do your disk modeling. And that's a different way. So with the arrows, I was showing you the case of 2 pixels. Now I'm showing you a full image where I'm doing the correlation of the entire image. And this is still NICMOS data. OK, so how do we go about regularizing it? Really, I think the first insight by David Lafrenière in 2007 was to say, OK, you can regularize it by using some pseudo-inverse function in Python, IDL, MATLAB, whatever you like to use. But really, the real insight is to say there is something more to it, because if you're looking for planets, you know they're localized in PSF that are like 4 or 5 pixels around. I mean, you know they're not really big. So what you're doing is you're computing your correlation in these big regions of the image. All right? So you kind of get the trend of how the model of your speckles based on kind of a big subset of the image. But then the subtraction part, where you're replacing the model of the empirical model of the PSF that you've built, you're only replacing it in this gray area here. And you're marching along your entire image. And this by itself prevents you to be in a lot of the pathological cases where you're subtracting all the signal or you're fitting all the signal. And of course, one of the drawbacks of doing this method with small, what we call subtraction zones, is you're really making the hypothesis that the hypothesis you're testing is there signal in a small box? So you're giving up on disks, but you're going to be really good at planets. And so when you read all these papers, and I'm sure you guys have read some of them, you see all these algorithm parameters. It's all these knobs you can turn to make the reduction look better or worse. And here, well, you have the geometry of the optimization zone. So it's two parameters, delta x, delta y, or delta theta and delta r. The geometry of the subtraction zone. Then you have the exclusion of the protection criteria, and I'll go back to that later, but that's in the case of ADI or spectral differential imaging. This tells you how much, how you choose your references depending on the presumed motion of a companion on your detector. And then you can do some SVD truncation, some LU decomposition of the correlation matrix of the optimization zone. And all these knobs, what you end up doing, it's kind of pretty empirical. You just turn them until you get what you want, and you're happy with your detection image and with the signal you're getting. There's some variants to that. You can just, instead of solving the least square problem, you can add a penalty term. That's something I showed, I think, in 2012, and I'm not going to get into detail. And then you can really do this A-Loci stuff, this adaptive Loci, where you're really searching the entire parameter space. That's something we did for the NICMOS data with Rémi Soumer, where this is the raw Hubble data, Hubble NICMOS. This is the straight-up target minus reference Psf subtraction. And then we charge ahead and we tried Loci with a whole bunch of possible parameters and geometries. And when you do that, you can, on your best images, retrieve the signal from HRD 79 B, C, and D in the two rolls. So these are two rolls of the Hubble telescope, two rolls that are 30 degrees apart. And then Thankuri pushed it to another level. I'm going to go back to this figure later. But this is this image here, where in this case, you reduce it for a set of parameters. And then you're kind of optimizing your parameters in either simultaneous annealing or steepest descent way in order to get the parameters that are giving you your best SNR map. And this is all through the same 6 or 7 parameters that I showed you earlier. Now, there's a second family of ways to go about it. And a lot of people, and even the way we're like splitting the hands-on session, you have Loci and then you have PCA. But it's solving the same least square problem. It's just a different way to do the regularization. There's nothing really fundamental that's different about it. The problem you're trying to solve when you do a PCA, you're not trying to minimize the coefficient per se. You're trying to find the best representation of your point spread function that that's a complicated one to actually explain. But when you're going to get these, what we call these eigenimages, and you're going to project your instrument response on these eigenimages, it's going to represent them best in the least square sense, with the least amount of modes. It's a little convoluted, but the whole point is you take your correlation matrix, and you calculate the eigenvectors for your correlation matrix. And you do some linear algebra on them, and you create these eigenimages here that just look like typical NICMOS point spread functions. Now, this is, for instance, so I think for this one we use like 400 NICMOS images. This means that in the 400 NICMOS images that I used, that pattern is the pattern that comes up the most often. And it's almost always there. Now, when you go to the 400th of these images, so here I have the first 5. If I went to 400, the 400th one would just be like a little noise there, which means, well, this one is really only in one image, and we don't really care about it, because if I'm going to take any random NICMOS image and try to do Psf subtraction, I'm going to care about this mode here, because it's always there. And this one is, I think one of those is the actual breathing of the Hubble Space Telescope as it goes 45 minutes around the Earth. So this is the actual algorithm. The nice thing, and that's why I like, the reason I use the algorithm, this algorithm, is not because, I came up with it, no. It's because I can wrap my head around what it does. And the reason I can wrap my head is I like to use the what we call the clip truncation, which is simply the number of modes. You can use these first 3 in this decomposition. You can use the first 50. But the noise in the residual image, as a function of number of modes, can be really predicted by a very simple relationship between the eigenvalues of the correlation matrix. And these points here are actually real points based on the NICMOS Psf. So, it's one of the cases where the theory actually matches what you're observing. And you can use this thing. So this gives you a proxy on what the residual noise in your image is going to be. you can just project the image of a planet, the prism image of the planet on these modes also. You just go to, for Hubble, you take a tiny team Psf, which is like a realization of what Hubble Psf looks like in that filter. And you can predict what the throughput of your algorithm is going to be. And so based on that, you can predict what the SNR is going to be. So that's a throughput, I think, for a point source. This one is for a face on disk. And you can make these plots here where, say, I mean, forget about these values here. They're not normalized properly of SNR. But say you have a suspicious blob in an image. And you're like, maybe it's something. I mean, if you have a very meaningful detection, you're set. But you have something, it looks really weird, and you just don't know how to go about it. And what I like to do is I just do the aperture photometry on this source here. All right? That's what it is. And then you do the aperture photometry on any 20 other sources or blobs that are around at the same angular separation. And when you increase the number of modes, so when you increase how much the PSF you're trying to take out, most of the time your noise is just going to go down where your signal is going to stay put, sort of. It's not staying put really well. And so this is actually a tool I'm using to discriminate when I have a 2 sigma detection and I'm wondering, should I spend another day trying to tease it up to 4 or 5 sigma? And this is actually, this just comes straight from the theory where you just have this function here and this one here. And these are those two here, except that this one is it's a log scale, so you don't really see it dropping very well. So the algorithm parameters, at this point, the other nice thing why I'm using this is this doesn't mean that you don't have to do the trick of using subtraction zone and optimization zone. You could do the same thing. In practice, I found that I can just get away without doing it. So you remove your computational. I mean, this is just so much faster because you don't have to deal with that. You could just try to use the full-blown with 2 different sizes of zone and play that game and really try to go deep in contrast. But in practice, I've never found it useful in the data that I've used. So less parameters to explore and a little faster, and then you have the same type of parameters here. And so this is a very, very nice figure. I mean, I really like this paper. This is the confirmation on the AG 95086. And they really went to town and tried a bunch of, 6 different pipelines to really confirm that this companion here was there in the NACOL band data. And the point that I'm trying to make here, if you're new in this business and you see a figure like this with all these names of different algorithms, it looks a little scary. But what I'm trying to convey here, and I think, that's the last slide of this part, is that this is all solving a least squares problem and picking the tool you're most comfortable with to actually see it. And it's there in all of them. I mean, the statistical significance of detection changes depending on which method you're using, but it's pretty much, the signal is there in all of them. So I'm not going to claim that they're all equivalent, but a lot of it is because you're solving a least squares problem, there's only so many different things you can do. Now, if you're changing your cost function, if you're going to go to different norms, if you're going to have more penalty terms, that's going to be a whole different story. But I don't think, on real data right now, nobody is doing that. There are papers trying to explore that, but everybody on real data is using least square fitting. So that's fantastic. We can, I've just told you that you can pick the algorithm you like and write it up, or take the code that you're going to get at the hands-on session and run away and reduce your own data. And that's going to bring you 10% of the way. Because once you have that nice detection, you have to write a paper and tell everybody else how bright it is, that companion is, and where it is on the detector, and all that shenanigans. Well, this example shows you that this is pretty tricky. If I want to write a paper saying, is there anything in here, I can probably write it and say there's nothing in here. If I really want to measure the surface brightness profile of this disk and figure out how many modes I need to use, okay, well, this looks better, but is it part of the PSF, or is it just part of the disk? This is not easy. And the reason is, it's this little thing here. I mean, this red arrow is not exactly this as aligned as with the purple arrow. And any of these methods, they're just screwing up your signal. So the next step, and actually one of the hard steps, and the one, I mean, most of us who are actually trying to use it spend the most time, is figuring out what the signal really is and figuring out real uncertainties on the signal. And while before I kind of gave you the story that these algorithms are all the same, the way they corrupt the signal is very different. And how you're going to choose which one you want to use. I don't think there is a consensus in the community on how to go about it. And this is a legitimate non-consensus. It's not an ego battle. It's just like we still don't really understand what's going on. We've made a lot of progress over 3 or 4 years, but there's a lot more progress to be made. So what I'm going to do here is I'm just going to go through each method very quickly. I mean, I have 15 minutes or so, something like this. 14, yeah. So I'm not going to go into detail of every little way to do it. And pretty much, you'll have the resources. And at the end, I have a slide with all the papers showing each method. And then you'll have pretty much, I'm hoping by the end of the hands-on session, you can make up your mind on where the trade-offs are. And then if you have your own data and you want to apply these methods, based on the experience you have in the hands-on session, you can go pick the right resources and use whatever you guys think is more appropriate to your science. So first technique, where you just inject fake sources in your data. And you're seeing how the signal on the fake sources is corrupted. So this is like, I think, this is done on Sphere data for point sources on Sphere lab data. And you can look at the astrometric precision of that you get. So this says you know where you put your source, so then you just find the centroid of wherever your source is in your radius image, and you can see how well you're doing, and you can also look at your astrometric precision. Sorry, your photometric precision here. And of course, it gets better. The farther away you go from the star, the easier it is. For a constant contrast at 10 to the minus 4. So that's how you do for point sources. For disks, you can actually, for these nice edge on disks, you can actually inject a fake disk in the data, in the same data. And with this argument about these zones, I mean, the signal is localized on this diagonal of your image. You're putting a fake disk based on your best model of what you think the disk looks like, and you're kind of figuring out what your reduction does to this fake disk is. Here. This is a little tricky. You need to have a good model of your disk, but at this point, I mean, this is beta pictoris. There were good guesses about what beta pictoris should be looking like, and so that's perfectly fine. Now, the tricky part when you do this, of course, is that you're kind of figuring out what the algorithm does to your disk in parts of the image where you don't have signal. So it might be that the speckles are very different here than here, and you're not really retrieving exactly what's happening. And in that case, if that's all you do, you say, well, you try different orientations for your disk, for your fake disk, and then you say, well, I'm going to live with the uncertainties of that, and that's going to be my error bar, and I'm writing my paper, and I'm happy. You could also inject negative fake in the raw data at the location where you think it is, and you could keep going with that. So it's something Christian Moreau proposed, and I think also that was done in the beta big disk where they tried both methods and found things that were pretty self-consistent. And I don't know where Julien is, but he can correct me at the end if I'm not saying the right thing. You can also, that was done also, I think, with this method that was presented in a pop session yesterday, where on top of this, they had this very clever scheme of doing it in terms of convolutions. I mean, one of the hard things when you do that, it starts to be very heavily computationally. So you have to play all these tricks. Anything you can write as a convolution, you can do it with Fourier transforms, and it just greatly speeds up your algorithm. And there are plenty of tricks you can play with that, but I'm not going to get into those here. Now, this is all good, but there's still some problems here. And in particular, in the case where I said earlier, right now we've been saying that your references don't have any signal. Well, when you're in this mode here, say in ADI, there's actually some signal in your references here. And there is some overlap, there is some crosstalk. That really screws up your signal. And it's even worse in the wavelength domain here. You could have some overlap between your two wavelengths. Now, when you're choosing your references, you're selecting the right ones that the overlap is not that strong. But it doesn't mean that it's not going to have some impact at some point on your signal, on the signal you extract. And this is a cute thing that was done by Tim Brand from Princeton a few years ago. So this is like the regular problem, assuming there is no signal. If there is some signal, then you're building your correlation matrix based on your reference image with this. Then you have some astrophysical signal, the model of the companion that's either turning as a function of PA offset or moving as a function of wavelength. So it's in your references. And that you can sort of predict. If you know these coefficients and you know by how much you're moving, then you can just deterministically predict what's happening. But on top of this, the fact that you have some more quote-unquote junk in your references, it's going to change your coefficients. So you have these 4 terms. You can neglect this one times this one because it's just 2 small quantities. But there is, Tim published this very nice scheme to actually retrieve each term here. And this is this figure here. This is just done for ADI, where you can retrieve each one of these terms and really model your self-subtraction in ADI. Now, it's in ADI, and there's something very special about ADI. So we're talking about the planet rotating on the field angle. If you try to do it in the spectral domain, so here you have a spectrum. And this is something from P1640, which is doing brute force loci, where this is the injected spectrum, this is a spectrum that comes out. Of course, it's a complete mess. And one of the problems is, it's what I said here. You have to choose your images carefully. But this is actually really important. In ADI, you can get away with some sort of contamination and calibrating it because the planet is it's the same brightness in each reference image. Once you start playing with this wavelength here, you have to really choose carefully which image you're using in your reference library. Because what's underlying in the contamination is actually the spectrum, the signal you're trying to extract. So it's becoming kind of a nightmare. The solution Christian Marois proposed this year, which is really nice, is to say simply, well, I'm going to, instead of doing this exclusion criteria where I just blindly remove, say, 3 slices before, 3 slices after, so these are the red slices that I just don't use in my reference, I'm going to calculate a priori how much contamination I'm going to have, assuming that the planet has methane. And if it has methane, then it doesn't matter. The longer wavelength, you use all of them because there is no signal. But the shorter wavelengths, you remove some of them. And you can play this game depending on what you think your spectrum is like to determine a priori your signal contamination. And then so that's what I try to write here, where you have the delta, the exclusion criteria in R is not the same on longer or shorter wavelength. So you do that, and then you just run the same least squares fitting, and this is the results he got with early GPy data. Now you can do the same thing, not sort of the same thing, but with the PCA algorithm, but I'm actually going to talk about it on Thursday in the talk about astrometry. Right now I'm going to present you the zeroth order approximation to do that, and it's all kind of hidden in this. Say you have some signal from your astrophysical signal, not exactly on the pixel in which you're looking for, but it's moved a little bit in my mess up your principal component analysis. And you see that the noise, the residual, goes deep very quickly. So if the signal of that companion happens to be in the higher modes, you've won. Because you don't need to use those to get a good SNR. Now, if they happen to be here, that's a different kind of worms, and that's what I'll talk about on Thursday. But this is a figure that Jonathan put together. This is the SNR as a function of number of modes for different wavelength for a P1640 source, and this is what you see on the spectrum as a function of modes. So from 0 mode to 20 mode, from 1 mode to 20 modes. And you can see that the spectrum here, it's actually pretty stable as a function of mode. So for this source here, actually, this one is nicer. This one, there's something weird happening. See, for the first mode, the signal is low. Then it's going up, and then it stays there. That means there's something really, really weird happening. This is what should be happening. The signal goes up, is high. So that's like at this point, the signal, which is the aperture photometry, it's just a speckle. Then it all drops down, and then it converges to this spectrum here for this source here. And so here, this one was done in a case where everything checked out, and we don't need to do anything a little more fancy. All we're doing is we're just actually changing the size of the zones on which we're doing the correlations to try to make sure that there's nothing pathological, but that we already went through that process. There are other cases where you just can't get away with that, and you have to be a little more careful. For these cases, for instance, you can use the S4 algorithm that was developed by Rob, who's going to co-lead the session with me, where the idea is that all I'm looking at is just patches of the image. What Rob realized is that you can look at patches, but more in the 3D space. So he's looking at patches as a function of 2D patches, but the x-axis is a radius, separation from the star, and the y-axis is the wavelength. And he's building the diversity of his patches by taking different patches azimuthally. And then you just build the basis of references. It's in a different space, but you subtract it, and that's what happens when you subtract one of these patches. When you do the PCA on one of these patches, so this is the original patch, this is reconstruction with k PCA modes, and this is your residual. And when you have a companion, you can see that your companion here, the trace of your companion in these patches is going to be this diagonal trace. This is the speckle that the companion, well, this is in rescale space, so the speckles don't move as a function of radius, while the companion moves as a function of radius. And you can use that to reconstruct your detection map and then actually fit a spectrum through this line. It's a lot nicer with the actual biases from your algorithm. You can also, solution 7, getting to the end of the talk, you can also use priors about the instrument. So this is what speckle deconvolution does. So it's just assuming that the speckle moves as functional wavelengths. You can just fit a low-order polynomial for chromaticity of the speckles. Marie Gouff proposed a method where you really build a model. Like this, we're getting to methods where you actually build a model of what your PSF should look like based on what you know in the instrument, where you jointly estimate the wavefront error and whatever your astrophysical scene looks like. And this is starting to be a little more, it's still in the least square sense, I believe. Marie can correct me if it's not in the least square sense, but it's starting to be a least squares with a lot of penalty terms. It's starting to be pretty hairy mathematically, but in the end, if you can really do that, then you don't have the problems of corrupting the signal, because you really, at the same time as you're estimating a signal, you're also estimating where your errors are coming from. This is something that was proposed by Olivier Guyen's group, where you actually record your science images and your telemetry, and you correlate them, and you build a dictionary in between those two. And this is what happens, where once you've subtracted the template created based on your telemetry, you can actually make high contrast images. And sure enough here, this is the way I like to think about it is we're regularizing the least squares problem with other information. We're using information about what we know about the noise properties. Whereas most of the other solutions I presented you is what you know about what the companion should look like or what the signal should look like. And so these methods, they're all more kind of new and not mature yet, but they're going about the problem in a way that, in my head, makes more sense. Let's get as much as we know about what the noise looks like before making assumptions and shortcuts about what the signal should look like. Unfortunately, we all want to write these beautiful papers, and so we're trying to take the shortcut and make priors about what we think the signal looks like. But this probably in this direction, there's a lot of growth, and if you're a lot young in this field, I encourage you to keep digging in that direction. So just 1 minute about the hands-on session. That's what I said earlier. For the detection problem, there is a magic recipe, which is pick your algorithm. They all have 6 or 7 different parameters. If you tweak the parameters well enough, all algorithms are equal. I mean, it's not really true, but you know. For the characterization, though, there was really no magic recipe yet. And I think that during the hands-on session, you're going to have, you're going to play and see what really all these methods do on the data. And then hopefully you're going to be able to choose between these solutions or the next one you guys figure out. And this is the list of papers that I had in here if you guys want to go there. Yeah. How do the algorithm behave in the presence of nonlinear detector noise? They don't. There has to be a nonlinear correction beforehand. Otherwise, everything is linear. So if you have
how linear is linear? 1%, 2%?
I think 1%. I mean, 1% is going to give you a 1% residual due to the nonlinear error. So if you're trying to gain a factor of 100, you're going to be stuck after you've removed your speckles by a factor of 100 by your 1% of nonlinearity. Yeah. And that's what we get. We get between like 10 and 100. So 10% nonlinearity would be pretty bad. So now, but I'm going to go to the figure first because, okay, this figure here. So Lynn is saying that, okay, they all pick up the companion, but some of them pick up a lot of junk, and some of them don't pick up junk. So my theory, and I was not involved with this paper, I think the first author of this paper is in the room, so he can call me on my bluff if I'm wrong. My theory is that if you spend enough time tweaking your parameters, you will really get rid of these blobs. And the particularity about this algorithm, that's what it's really trying to do. It's doing a steepest descent on the algorithms, on the parameters to really, really get it. But I don't know. Maybe Julien Rameau, who's somewhere here, can say something about it. So what Julien is saying, there's also a matter of how far you are from the star. Some algorithms are really good far away from the star, but if you go close in, they're really starting to have trouble. And actually, I mean, let me take that back. I think none of these had any optimization, right? You were just doing ADI, choosing your references, and doing a median. There was no coefficient optimization for those two. Yeah.
What is that one that?
This is a loci, so which is you really do the steepest descent on your algorithm parameters. Well, I think what it probably does in theory. Now, once you've really nailed down whatever best parameters gives you this detection, I think, I mean, there's a lot of papers, so I tried to read everything, but I think mostly what Thane does, he gets to something that's really close to Tim's approach here with the perturbation method. So then you can retrieve, you lose a lot of the flux, but you know how bad it is. So even if it screwed up your flux, if you can calibrate it, and part of the last part of my blurb was, for ADI, actually, this is pretty much done because your flux is the same in every reference image. Once you use the spectral information, you're actually, what you want to measure is corrupting really the relative weight of each wavelength. It's not just going to be how close or how far, it's not just going to be this picture here. There you go. Do you make them overlap or not? Because if there's no flux in this image here, you can make them overlap as much as you want. It doesn't matter. I mean, this is the methane case where it doesn't matter if there's methane. You just make them overlap. So this is when it becomes a little trickier. And that's why IFUs is going to make our life a little